Welcome again to our simplified chemistry lessons. Today we are looking at another interesting topic in Form 2 called carbon and its compound. My name is Simple Teacher. In this topic of carbon and its compounds, we look at carbon itself and then its compounds. Let us start at looking at carbon. So carbon is an element in group 4 of the periodic table, has 6 electrons, so electronic configuration is 2 4. So it's that tetravalent, has a valency of 4. In terms of sources, it can be gotten from its allotropes, the common ones being diamond and graphite. It can also be gotten from amorphous compounds such as coal, charcoal and coke. It can also be found in carbon 4 oxide that comes from the atmosphere. As you know, in air, carbon 4 oxide is 0.03%. Let us look at the comparison between the two common allotropes of carbon, which are carbon diamond and carbon graphite. The difference is, one is that diamond is shiny crystalline solid, while graphite is black or dull crystalline solid. Two is that diamond has a very high density. It is one of the hardest substances, while graphite is soft. Diamond is abrasive, where graphite is slippery. Then that is in terms of texture. In terms of structures, diamond has a strong giant tetrahedral structure. That's why it is one of the hardest substance, while graphite has a giant hexagonal structure. Remember, we said the diamond from the topic of structure and bonding has a layered hexagonal structure, where it has layers that are joined together, not with a very strong bond, and that's why it is slippery. In terms of similarities, both have a very high boiling and melting points. In terms of uses, diamond is used to make jewels for drilling and cutting of metals, while graphite is used to make pencil leads, to make electrodes, and also as a lubricant. Now let us look at the properties of carbon. One, appearance, it is black solid. Solubility, it is insoluble in water. Electric and thermal conductivity, very poor. Burning of carbon in air or oxygen. In excess air or excess oxygen, it forms carbon 4 oxide. But with limited oxygen or air, it forms carbon 2 oxide. The carbon 4 oxide formed when the air is excess can be dissolved in water to form a weak acid called carbon 4 acid. All these are represented in the chemical equations that you can see as being presented here. Another property of carbon, it is a reducing agent. So it reduces metal oxides to metals, and itself is oxidized to carbon 4 oxide. So what happens is that when it is reacted with oxides of copper, zinc, lead and iron, it deprives the oxygen, and it becomes carbon 2 oxide, while the oxide is, after being deprived, the metal, it's only the metal that remains. You can see here the example of copper oxide, which after reacting with the carbon, it remains copper, and then the oxygen in it combines with the carbon to form carbon 4 oxide. Now let us look at the reaction with the concentrated acids. It reduces both the nitric and sulfuric concentrated acids to the gases. For concentrated nitric acid, it is reduced to nitrogen 4 oxide gas, and the carbon is oxidized to carbon 4 oxide. And for concentrated sulfuric acid, it is reduced to sulfur 4 oxide, while the carbon is oxidized to carbon oxide. Water is also produced in both of these reactions. You can see the chemical equations as presented here. Now let us look at compounds of carbon, and we start with carbon 4 oxide. Let us look at how it is prepared in the laboratory. This happens when calcium carbonate or marble chips is reacted with hydrochloric acid. You can also react sodium hydrogen carbonate with hydrochloric acid and be able to get the carbon 4 oxide. The setup is per the diagram that is being presented here. You can see dilute hydrochloric acid goes down through this through funnel and reacts with the calcium carbonate down here. So a gas is produced which is passed through water and then through concentrated sulfuric acid, then collected through downward delivery. Some notes. Purpose of water in this setup is to help absorb the hydrogen chloride fumes that are produced during this vigorous reaction. The purpose of concentrated sulfuric acid is, of course, to dry the gas. Remember, concentrated sulfuric acid is a very good drying agent for gases. The collection method, as you can see here, is downward delivery or upward displacement of air, is because carbon 4 oxide is denser than air. So the reaction is, as you can see in that equation. Something else to note is that dilute sulfuric acid cannot be used to replace dilute hydrochloric acid in this setup. This is because there will be formation of insoluble calcium sulfate that will cover unreacted marble chips and stop further reaction. So there will be very little reaction and therefore very little gas will be produced. Also, you cannot use lead 2 carbonate instead of calcium carbonate. Is because there will be formation of the insoluble lead 2 chloride, which will cover the unreacted lead carbonate and stop further reaction. So even here, very little gas will be produced. Let us look at the properties of carbon 2 oxide. One, the physical properties: it is colorless, it is odorless. Number 2 is that for its confirmatory test is that when it is reacted with lime water or calcium hydroxide, there is formation of a white precipitate of calcium carbonate. This we have discussed even before in other topics, and this precipitate can dissolve if you put excess carbon 4 oxide due to the formation of calcium hydrogen carbonate. The reactions, you can see the equations that are presented here. Now, in terms of another test, is that it extinguishes a burning splint. So those are the two confirmatory tests. Now we look at the other properties of carbon 4 oxide, and another one is effect on litmus paper. When you put dry blue and red litmus paper on a gas jar filled with carbon 4 oxide, there is no change. Wet blue litmus paper changes to red, faint red. Then wet red litmus paper does not change. The reason why wet blue litmus paper changes is because the carbon 4 oxide reacts with the water or reacts with water to form carbon 4 acid, like we have described earlier. Now, support for combustion generally does not support combustion, carbon 4 oxide. However, magnesium, because of the way it is exothermic in its burning, it burns with a lot of brightness, producing enough heat to decompose the carbon 4 oxide into carbon and oxygen. And now the oxygen that is generated from that decomposition, it continues to burn the magnesium to form magnesium oxide, which is white. Then some black specks, charcoal specks, are formed on the side of the reaction apparatus. This because some carbon is produced as carbon 4 oxide is reduced to carbon. So the carbon 4 oxide is reduced to carbon while magnesium is oxidized to magnesium oxide. This is as per the reaction that you can see here in this chemical equation. Now we look at the uses of carbon dioxide. One is in Solvay process, in manufacture of soda ash. It is also used to preserve aerated drinks. It's also used to make fire extinguishers. As we have said, it doesn't support combustion. That's why it is useful in making extinguishers. It's also used in manufacture of baking powder and also in photosynthesis, the process by which plants make their own food. So now let us look at the other compound of carbon, which is carbon 2 oxide. In terms of preparation in the laboratory, it is prepared through dehydration of methanoic acid or oxalic acid. This is done using concentrated sulfuric acid, and some heating is done. In terms of the setup, as you can see there, I'm displaying a setup for dehydration of oxalic acid, where as shown there, there is concentrated sulfuric acid coming down into the flask and reacting or being used to dehydrate oxalic acid, and therefore producing carbon 2 oxide, which is passed through some potassium hydroxide and then collected through water method. So the purpose of the sodium, or you can use sodium or potassium hydroxide here, is so that it's to absorb a carbon 4 oxide that is produced during the reaction. Remember, here we just want to collect carbon 2 oxide. Therefore, any carbon 4 oxides that is produced must be absorbed. So potassium or sodium hydroxide is used for that purpose. The gas is collected through water. Of course, it is because it is insoluble in water, and also you can see it is the gas jar is facing downward, so it is upward delivery through water. And the reason why it is possible to collect it through upward delivery of water is that one, it is insoluble in water, and two, it is less dense than air. Let us look at the properties of carbon 2 oxide. One, the color and smell. It's colorless and is odorless. Effect on litmus paper, no effect, whether it's wet, whether it's dry, whether red or blue, because it is a molecular compound and so does not ionize to release hydrogen ions. In terms of combustion, it combines in air or oxygen with a blue flame to form carbon 4 oxide, as per the equation you can see here being displayed. It is also a reducing agent, so it reduces metal oxides to respective metals, and it is oxidized to carbon 4 oxide. An example is the one I'm showing here, where it is reducing copper oxide to copper metal, and it is being oxidized to carbon 4 oxide. It is a pollutant and it is highly poisonous. It's because when it enters the body, it combines with hemoglobin to form carboxyl hemoglobin in the blood. So now what happens, instead of blood circulating oxygen, it circulates carbon 2 oxide, which now without the oxygen, the human person or any living organism will experience nausea, coma, and then death. So instead of having hemoglobin in the body, you have carboxyhemoglobin, which now affects the rate at which oxygen is transported to the different parts of the body. Let us look at how it causes death, or it is created while a burning charcoal is put in an enclosure where there are living organisms. As you can see, this is a setup for the charcoal. Air enters through the air hole. You know how the charcoal is. There is that space that is left open where the air enters in. So when air comes in, it comes up here to where the where the charcoal is. Remember, charcoal is carbon. Then once the air reacts with carbon here, it forms carbon 4 oxide. This is because there is plenty of air down here. But then as the carbon 4 oxide form goes up and up here, there is a lot of carbon here. So that carbon 4 oxide is reduced to carbon 2 oxide. So by the time it is reaching up here, it is a lot of carbon 2 oxide, and now it requires to get enough air up here for it to be converted back or to be oxidized to carbon 4 oxide. But now if there is no plenty of air in the room, the air that will continue being come out from the GCO will be carbon 2 oxide. And as we have described, carbon 2 oxide, when it reaches the body, it interferes with the flow of oxygen to body parts, which causes nausea, coma, and then death. So at different levels, now you understand what happens. Down here there is carbon 2 oxide. Then as you go up there, carbon 4 oxide, sorry, as you go up there, it becomes carbon 2 oxide. And finally here, if there is plenty of water, it is carbon 4 oxide. If there is not enough water, air, sorry, it is carbon 2 oxide, which is poisonous. So that is the process of carbon 2 oxide formation, and how the GCO is able to produce carbon 2 oxide, and which is poisonous. The confirmatory test for carbon 2 oxide is that you burn it in oxygen to form carbon 4 oxide, which now you pass through the lime water to confirm that it produces a white precipitate. So uses of carbon 2 oxide: 1, it's used to extract metal ores such as iron, zinc, lead, and copper, and it is also used as a fuel. Now let us look at other compounds of carbon called carbonates and hydrogen carbonates. Carbonates are normal salts derived from carbonic 4 acid, while hydrogen carbonates are acidic salts that are derived from carbonic 4 acid also. So carbonic 4 acid, or H2CO3, is formed when carbon 4 oxide gas is bubbled in water, as we have described earlier. It is a diabasic acid with 2 ionizable hydrogen, as you can see in those in that equation there. So this is formation of carbonate, and here hydrogen carbonate. Now let us look at the properties of both carbonates and hydrogen carbonates. In terms of solubility, carbonates are insoluble except sodium, potassium, and ammonium carbonates, and hydrogen carbonates are all soluble. Effects of heat on carbonates: for sodium and potassium carbonates, they do not decompose. Other carbonates, they decompose to form a metal oxide and produce carbon 4 oxide. This, as you can see in this example here, magnesium carbonate is being decomposed to magnesium oxide, and carbon 4 oxide is produced. For hydrogen carbonates, they decompose to form the respective metal carbonates, water, and carbon 4 oxide. An example is the one I'm displaying here about ammonium hydrogen carbonate and calcium hydrogen carbonate. Another thing we are looking at here is the confirmation test for both carbonates and hydrogen carbonates. If you have a compound or a substance that you want to determine whether it is a carbonate or a hydrogen carbonate, what you do is that one, you mix, you react that particular substance with lead 2 nitrate is the first step, and if a white precipitate is formed, it is either a carbonate, a sulfate, or a chloride. So then after that, you add 6 drops of dilute nitric acid and preserve. If the white precipitate dissolves, then it could be either a carbonate or a sulfite. So the third step is you add 4 drops of acidified potassium manganate 7. If acidified potassium manganate 7 is decolorized, then it is a sulfite. And if the acidified potassium manganate 7 will not be decolorized, then it is a carbonate. So that's how you determine if a substance is a carbonate or not. So now let us look at another compound of carbon, which is sodium carbonate. Sodium carbonate, or what we call soda ash, is normally produced through, naturally occurs, in Estrona in Lake Magadi in Kenya. And the formula for the compound is as I'm showing here. So what happens is that this trona, its solubility decreases with increase in temperature. So during the day, it's not soluble, it crystallizes in the lake, and it is then dug, put in a furnace where it is decomposed into soda ash or the sodium carbonate, and is put to bags and sold. So the process is represented by this equation. This is trona, then it decomposes to sodium carbonate, water, produces water and carbon dioxide in the process. So the uses of sodium carbonate is one, it is used for making grass, then it is used for softening of hard water. It's also used to manufacture of soapless detergents. It's also used in swimming pools to increase the pH. In the lake, the same lake where there is trona, there is also sodium chloride. And this sodium chloride, its solubility decreases with decrease in temperature. So at night, it is able to crystallize from the mixture or from the solution. It crystallizes, and it is mechanically dug. It is put in bags and sold as animal feeds or used to season foods. So there is a representation of the process of extracting both the trona and converting to sodium, and then decomposing to sodium carbonate, and also extracting sodium chloride. So as we have described, in the lake there is this mixture of sodium chloride and trona. Then through natural fractional distillation, they are separated, because at daytime you are able to get trona as we have described, and at night you are able to get sodium chloride. These are then dug, they are dredged, they are crushed. After being crushed, for sodium chloride, it is just extracted at that point, and it is now put in bags for selling. For trona, it has to go to the furnace so that there is decomposition to get sodium chloride from trona, and then carbon dioxide and water are released as byproducts during this process. So that is the graphical representation of the process. Now let us look at the industrial process of manufacturing sodium carbonate. This process is called Solvay process. And in this process, there are 4 raw materials. One is brine, or concentrated sodium chloride. The other is ammonia. The other is limestone, which is calcium carbonate or coke. And water is also a raw material. So those are the 4 raw materials. I want us to go through the process and what happens at the different stages and the processes that take place. Let us start with ammoniation. As you can see in the diagram, the 2 main raw materials are coming in at this end. One of the raw materials is brine, the other raw material is limestone. In the ammoniating tower here, this brine comes in, and then ammonia is mixed with ammonia to form what is called ammoniacal brine. So this is the process that is called ammoniation. It is the first process. So in this process, ammonia is being mixed with brine to form ammoniacal brine. Then there is a process called thermal decomposition. This happens at this chamber here called kiln. In kiln, the limestone that is coming in as a raw material is decomposed through heating to form calcium oxide and carbon dioxide. So here limestone is decomposed, calcium oxide is produced, and carbon dioxide is also produced. That process is called thermal decomposition. As you can see, the equation is well presented here. So what happens, the calcium oxide that is produced here goes to the next stage, or to the next chamber in the process called silica, where the carbon dioxide is pumped to the carbonator. Now let us go to the carbonator. Here we have the ammoniacal brine, and we have carbon oxide coming to the carbonator. In the carbonator, there is a process called carbonation. What happens here is that the ammoniacal brine from the ammoniating tower here reacts with carbon 4 oxide from the kiln, as you can see here, and water that comes in at this stage in the carbonator. Of course, this carbonator is also called the sulfate tower, to form ammonium chloride and sodium hydrogen chloride. So at this stage, there is formation of ammonium chloride and sodium hydrogen carbonate, and the equation is as presented here. So now the sodium hydrogen carbonate is less soluble than sodium chloride. So what happens at it crystallizes down the chamber, and while the ammonium chloride of course remains as a filtrate or as a solution, when the ammonium hydrogen carbonate crystallizes down. So both of them are pumped out and taken to the filters. So that process is called carbonation. Now from carbonation we go to filtration. Both the sodium hydrogen carbonate and ammonium chloride come to the filters, where now ammonium chloride becomes the filtrate after filtering, because it is the one that has not crystallized, while sodium hydrogen carbonate becomes the residue. Now after separation, the ammonium chloride is pushed down to another chamber called ammonia recovery or ammonia generator chamber, while now the sodium hydrogen carbonate moves straight to the roaster for the final stage of production of sodium carbonate. So that process that happens there in the filter is called filtration. Now we go to slaking. Remember, we said that from kiln the calcium oxide goes to slaker. So what happens in the slaker? Here the calcium oxide is mixed with water to form calcium hydroxide. So water comes in here, mixes with calcium oxide to form calcium hydroxide. So that process is called slaking. The equation is as presented there. So the calcium hydroxide that is formed is pushed to the ammonia recovery or ammonia generator chamber. Remember, here we also said that the ammonium chloride will come from filter, will come there. So what happens at the ammonia recovery? There's a process called ammonia regeneration here, and what happens here is that the calcium hydroxide from slaker is reacted with ammonium chloride from filters, and calcium chloride is formed, ammonia gas and water. So the equation is as presented there. So provided that the calcium chloride that is formed here becomes now a byproduct. It is churned out, as a byproduct and used as a drying agent. Ammonia gas is recycled back. It goes back to the ammoniating tower to be used, mixed again with brine to create ammoniacal brine. So that's what happens in this stage of ammonia regeneration. Now we go back to the roasting. The byproduct we said from after filtering, we got sodium hydrogen carbonate as a residue. So we take it to the roaster where the roasting happens, or it's also thermal decomposition, where here the sodium hydrogen carbonate is dried and decomposed at 300 degrees centigrade to produce now sodium carbonate, which is the final product, and also some water is produced and the carbon 4 oxide. So that is the equation that of the what happens at the roasting, at the roaster, of course. So this sodium carbonate is released as the final product, while the carbon 4 oxide is recycled back to the carbonator to be used at the stage here of carbonation. So that is the process of Solvay process, the manufacture of sodium chloride industrial manufacture of sodium chloride. Now let us look at that is all for this topic of carbon and its compounds. Of course, so many questions are brought from this topic in KCSE. So we have picked a few from the last few KCSEs that have been done. You can see in KCSE 2020 paper 1, there was a question on sodium carbonate is prepared on large scale by Solvay process. The equation for the main reaction that takes place, you can see it there. Describe how the sodium carbonate is obtained from the products of the carbonator. Now you can be able to explain what happens from carbonator up to the point where the sodium carbonate is produced. One of the byproducts of Solvay process is calcium chloride. Explain how the calcium chloride is formed in this process. You can be able to do it because that's what we have just looked at. KCSE 2019 paper 1. During laboratory preparation of carbon 4 oxide gas, dilute hydrochloric acid was added to substance L. You know which substance is that, and you can be able even to write the equation. And also you can state the observation made when the gas produced was bubbled through calcium hydroxide solution for a long time. It's a very simple question. KCSE 2021 paper 1. Study the setup below and answer the questions that follow. State the precautions that should be taken in carrying out the experiment. Give a reason. And state the observations made at the boiling tube in the boiling. Those are questions you look at, and at some point, as I keep saying, you'll be able to come back and do all of them. So carbon 2 oxide can be prepared by dehydration of ethanolic acid. Complete the equation, following equation to show the reaction that takes place, and then also name another reagent that can be used to prepare carbon 2 oxide by dehydration. So those are questions you can be able to answer. Thank you very much. That is the topic on carbon and its compounds. I want to trust that we have made it simple, and now it's easier to tackle the questions from this topic. So see you next time when we look at another topic.